On.
See comments on my PR. My PR documentation.
No, sorry. I was only basically what I was working on. The human basically. Significantly, what we have in
שומעים אותי?
this branch, this model source
שומעים.
makes changes in okay.
עוד נשאר לקוות שהדובר יגיע.
Guys, thanks for your time. See you. Only take me 5 minutes.
שירגיש מעל, היה שם גם ראשון והוא גבוה מדי, 5 ומינוס 5 בסנטר אחר. אני מאוד צריך לתפקיד של שתיתן מעל שליש מזה.
אוקיי.
Hey, Aviv.
Hi, Pulkit. Thank you for coming here.
Yeah, no worries. Thanks for inviting.
Yeah, is it okay with you if I record a talk?
Yes, perfectly okay.
Okay, great. So good. It looks like we have a nice attendance so far. Let's wait a couple more minutes and then we'll start.
Okay, so maybe I can just test my screen sharing.
Yeah, perfect.
See my screen?
Yes, it looks perfect. We also see your pointer. So,
can I just see if the videos are coming through fine?
Okay, we make these golden fluffy pancakes.
yeah, that looks good.
Do you also hear it?
Yes.
Perfect. Okay.
All right. So I think recording has been started. So I think we can start. Let me introduce Pulkit. So Pulkit is the Stephen and Rennie Finn Chair Professor in ECS at MIT, and he's the director of the Improbable AI Lab. And he works on robot learning generally, and he does some amazing works. He's won many awards. Too long a list for me to mention, but I'll just mention that he won the Coral Best Paper Award last year, and I hope that he's going to also tell us about that work today. I've seen some of the things he's trying to talk about, and it's amazing, and I'm really looking forward to this talk. So, okay, the stage is yours. Thank you for coming.
Thanks a lot, Avi, for inviting, and thanks a lot for the kind introduction. It's a pleasure to be here. So, the talk, let's make it interactive. So if you have questions, feel free to stop me, right? And, I'm not sure if I can monitor the chat, but if you just, raise your hand and speak out, I'll be happy to stop and answer your question. Right, so, a lot of us have had this dream that we want to be on the couch or to be in our home and want our robots to cook food and do many things that we do in a household, right? So for a moment, let's imagine how is the system going to work, right? I'm on my couch, get me a toast. And this robot should ideally do it, right? But this is a very abstract instruction for which, to execute this needs to be broken down into smaller steps. For example, go to the refrigerator, open the door, fetch the bread. Now, there is some very exciting progress with large-scale language models where people are showing that you can take abstract instructions and break them down into sub-steps. There was a SECAN paper which came out of Google. There was a couple of other papers coming out of other labs. Now, whether language models will always work, it's a question which the field will answer in the future. But for now, let us assume, let's cross our fingers and assume that this actually worked. And we got an abstract instruction, it was broken down into sub-steps. Let's see what the robot would do if it got such instructions. Right, so I'm showing you a clip from a movie where a robot got instructions of how to make a pancake. Let's see what actually ends up happening.
Okay, to make these golden fluffy pancakes, add flour, milk, and eggs.
You would probably never put eggs like that.
Mix thoroughly.
The robot is very happy.
Still lumpy. Marvelous.
That's what he thinks.
For crisp yet moist potatoes, brown on one side, then turn over. This will be some good slop.
Is something burning?
So it never realizes, right, that it needs to take out the toast out of the packet and then, then put it. And when you say, rotate it, it means rotate just the toast, not the pan with the toast. Right. So the point being that even if we could get to these concrete instructions, there's a lot of common sense knowledge which goes into actually executing them, right? So one model that we typically have is, there is language, it goes to a high level plan, and then the low level skills which executes them. And typically what we might think is that language is the hardest part to communicate in language. And, coming up with a high plan is maybe hard and the low level skills should be easy, right? But let's, pause for a moment and actually, look at evolution, right? Starting of life, it took us around 3.5 billion years to evolve apes, right? Which, maybe you can say they can do some low level skills, right? They can jump around, walk, use some tools, right? And then from apes to humans, it took around 18 million years, orders of magnitude less time. Then for language to evolve, it maybe took 50 to 500,000 years. Again, in orders of magnitude less time. Right. So in some ways, evolution took a lot of time in evolving low-level skills and exponentially less time to do high-level planning and language. Right? So this observation is commonly noted in AI as the Moravic's paradox. Right? What does this say? That contrary to traditional assumptions, reasoning requires very little computation, but sensory motor and perception skills require enormous computational resources. It's almost, when we walk and when we use our hands, we don't really think. The reason we don't think is because it is so big into us in evolution that we don't need to think, right? Or in simpler words, this is what Steve Pinker said some time back. The main lesson of 35 years of AI research is that the hard problems are easy and the easy problems are hard, right? What does this mean is that anything that you don't have to think about as a human is really hard, right? And everything that you really think about is maybe quite easy, right? So in the sense of Moravic's paradox, what is actually hard are these low-level skills. Once we have the low-level skills, it should be easy to stitch them together to build a high-level plan, and maybe even easier to operate it from language, right? So, with this perspective, what I'm going to present mostly is work on how to learn low-level skills. This is what most of this talk is about, right? Because our belief is that if we can get the low level right, going at the higher level should be much easier. So, let's begin with an example. And, a very common low-level skill is tool use, right? We might want a robot to, maybe cut something. But if we look at robotic systems today, they have a very peculiar way they use tools. Over here, if you see, this knife is rigidly attached to the robotic hand or to the robotic arm. Now, this is not, like an example in minority. In fact, most robots which use tools rigidly attach them to it. This is because we really don't know how to have robots use tools, right? So let's look at this problem. So if we have to use a knife, what would we need to do? First, we need to grasp it. Then we might need to reorient it so it's in the right position so I can actually execute the cut. And then we can actually go and cut it. Now, grasping, there's a lot of progress in this topic. And if there's a single object on a table, we can get accuracies on the north of 90%, even 95%. But then there's this next step. If I just grasp this knife, I cannot really use it. I need to turn it around in my hand before it actually becomes useful, which leads us to this problem of reorientation, which is much harder. Now, reorienting objects has been a popular topic of research, right? There are videos, this is a video from some labs in Japan, more than 20 years ago, really manipulating, this long pipe in a very dexterous and what appears a very meaningful way. Most recently, there was demonstration from OpenAI where they were, reorienting this cube in the hand. But if you were to look at these systems more carefully, they're stymied with many limitations, right? I mean, the reason this problem is hard is because this is high dimensional and there are discontinuities which come from contact. But most of these systems, and there are many of them, which I have not gone through, they either work with a very few number of objects, pretty much the only objects that you see on the screen, and they're operating with an upward-facing hand. And many times, to get the state of this object, there is this, very big sensing equipment that is put. What I mean by that will become clear. But let's first try to solve, these two issues, and let me lay them down concretely. Right, what we want is we want a system which can work with many different objects. We want it to work with hand facing upwards or hand facing downwards, right? I mean, many times when we go, we just, our hand is facing downward, we go pick up an object, right? You might say, well, what's the big deal with the hand facing downward? The fact is that the hand is facing upward, there is gravity which supports the object. But when the hand is facing downwards, the gravity is actually against us and the exploration becomes really hard. Right? Because there is no supporting force to be had. So the hand facing downwards is actually a problem where the object is almost always in an unstable configuration. And the third constraint we want to make is that the system should actually work with real world observations. Now, what do I mean by real world observations? Are things that we can actually measure with sensors that we can put on a practical system. Right? For example, I can tell what the target orientation is, what the joint positions of the fingers are, which we can read off motor encoders, and maybe we only have access to vision, right? Say RGBD or a point cloud, or maybe access to an object pose system, right? So these things we can maybe measure in the real world with minimal instrumentation. And what I'm going to show is, how do we satisfy all these three criteria and build a system which can reorient many objects, first both in simulation, and then we will move to some real world experiments. Right? So the first question we're going to ask is, how do we reorient many objects with real world observations? So this was work led by Tao and Zhe, who are two PhD students. So, how to deal. So now if we have to deal with different object shapes, right, we might intuitively think that we really require to reason about the exact shape of the object, the exact geometry to move our fingers. But many times in research, it's good to start with the simplest setting. So we're going to start with the simplest setting. We will not provide any shape information and see how far we can get. So the problem setup is going to look like we have a goal pose that we want to get to. The hand has the object in some position, and we want to learn with real world observations. Now that influences the design of the state space. So what states, and from the state, we have a policy pi theta, which maps states to actions AT. So what is the state in the real world? That is the joint positions, which are going to denote by QT, the object current pose, and the goal pose of the object. And the action space is going to be changed in the joint positions. So this is, my joint position at next time step is joints at the current time step plus the action and some time step. And we're going to run this at 20 Hertz. Now, yes?
Does this mean that you're not controlling the forces that you're applying on the object, or is it like somehow implicit?
So we are not controlling the forces directly, right? But this is, position control. So if I ask it to go inside, so if I command a position inside the object, then the finger will try to move, and that will implicitly apply a larger force.
I see.
So there's implicit force control, but nothing explicit over here. Any other questions? Is the setup clear? Okay. So then the rewards we're going to give is the difference between the current pose and the goal pose. And we're going to put a regularization that the object should be small, right? So that's the setup. Now for training, we're going to use a bunch of different objects and train a single policy which can work across all the objects. And we're going to leverage off-the-shelf, model-free reinforcement learning to be precise PPO over here. So now let's look at how well does the system work, right? So what I'm plotting on the y-axis is the success rate, and on the x-axis is the number of time steps. Note this is all in simulation, right? And the success rate that we get is around 70%, right? And we're defining something to be successful if the object is within 6 degrees of the goal position, right? So on one hand, 75% isn't really that great, right? It's better than 0, but not that great at all. It also takes a lot of time steps to get to this performance. So the natural question is, how can we actually go and improve performance? So the insight over here is that, well, there is some things which are available and that we can measure in the real world. But because we can train in simulation, there's a lot more information that we can actually exploit, right? For example, we can get accurate estimates of joint velocities instead of getting erroneous estimates by differentiating the joint positions. We can exactly get the fingertip velocities and many other things which might be harder to estimate. So these things might be hard to estimate in the real world, but are easily accessible in simulation. And and because these are easily accessible, we are going to exploit it because we think these are useful for the task. So this is what I'm going to call the full state, and then train a policy from this full state, right? And the same paradigm as before, and we're going to call this policy as the teacher policy. So now if we compare the performance of the teacher policy, what we find is it not only performs much better, but also it learns much faster, showing that privileged information is actually helping both the performance and the training speed. So now we have the teacher policy, but unfortunately we can't really deploy it, right? What we can really deploy is the student policy. So now what we're going to do is we're going to use the teacher to teach the student. And this is what we're going to do through imitation learning, specifically Dagger. What does Dagger do? It puts an L2 loss or a loss between the actions. So the goal is for the student to match the teacher's actions. So, now let's see how well does the student policy does, right? So we're going to train this on this data set of, around 2000, different objects and deploy it on these, 78 common household objects, which are part of the YCB data set. So if we look at the student policy, first on the training set itself, we get success rate around 96%, which is very close to what the teacher actually got. Right? Then we can, test on a different object data set, right? And this is the performance of the policy zero shot, right? There's no fine tuning, nothing happening. We just give new objects and see what the policy does, right? This is one more example. And, there are, more examples, right? And what these experiments are pretty much showing is that we are able to reorient a diverse set of objects. Now, when we go to the zero shot regime, the performance does drop something, it's around 70%. A part of it is also because the objects in YCB are harder than the objects in the EGAD dataset. So, what have the results until now told us? Right? The results until now have told us is that privileged information is useful. The student-teacher paradigm is a good way to exploit privileged information. Right? And maybe a surprising finding is that we're able to reorient many objects without knowing anything about their shape, right? Which was very counterintuitive to me, at least initially. Right? But now, let's jump ahead and see, well, can we do this only in the simple case of the hand facing upwards? Or could we also do it when the hand is actually facing downwards? Right? So now if we take the same framework, but apply it in this more challenging scenario, what we find is the object almost always falls down. So this approach that I described doesn't really work. Right? And then, you scratch your head and it's like, why is this not working? Right? So, one thought you might have, or we had is, well, are we really trying to solve an impossible problem? If you look at the hand in the current configuration, there is no way there exists a feasible set of actions to actually close the fingers to grab the object. It's almost always going to fall down. Right? So what we were doing was we were initializing the objects randomly in the hand, but that doesn't mean that those initializations are feasible in the sense that the object is going to fall down. Right? So the intuition is very simple. First you grasp the object, that is what we do as humans, and then you reorient them, right? So reorient after stable grasping. So one can go ahead and, we can train policies, which can go and grasp objects, right? So over here, I'm just showing, some rollouts from a policy, which can grasp, new objects. And now we can, start doing, reorientation. So what you find over here is, this hand, reorienting again new objects that it was not really trained upon. So, okay, so these results, look promising. Okay, so we can get, some success in getting, reorientation to work also in this harder setup. Let's go back and see what the performance is. So what we found in EGAD, right, in which we trained, the teacher was around 82% now. It is lower from 96 we were getting with the hand facing upwards, and the student is closely following the teacher, maybe 10% behind. But on YCB, we're getting a big hit in performance, right? It's only around 45%. So then the question becomes, can we make it even better? And the intuition again goes back to the fact that we can really exploit the simulator in many interesting ways to make the learning be easier. Right? So what was the most challenging thing in reorienting the object with the hand facing downwards? Right? It was the fact that gravity makes the object be an unstable configuration all the time. Right? What if I could switch off gravity? Right? Then the task should be easy. Right? So maybe I can make the task be easy first, and then slowly increase the complexity, right? This popular idea of doing curriculum learning. So what we did was, we initiated this curriculum over the gravity, where we start with zero gravity and, we go to normal gravity. But this is something we can do because we're in simulator, right? So we can really exploit the simulator. If we do this, we get, a big jump in performance. So it goes back from 45 to around, 70% that we were seeing with the hand facing upwards, right? So by exploiting the simulator, we were able to build a policy which can reorient pretty much, any object you give it. Not 100%, but still, at 70% if you want to be within 5 degrees. Right, so this is just one video of the hand continuously reorienting these objects. Right? And there are more videos of the hand reorienting different objects. And surprisingly, the observation that we had made initially, that we require no object shape, actually holds true even now. So what I'm going to do now is take a small pause and see if there are any questions.
I have a few questions, if that's all right.
Yes.
So I have 2 questions. The first one, do you assume any friction with the objects while using the hand?
Yes, there is friction.
But not, you still assume that you have to hold it, but it wouldn't slip away from you just by not doing anything if you just hold it upside down.
Well, if the fingers don't apply the right force, it will slip down.
Okay. And my second question is: do you consider the maximal strength that you can put on a single object, let's say a paper cup or something? Do you consider like this is the maximum strength I can put on it, not any more than that?
Not for now. I mean, the one reason is we don't have tactile sensors on the hand, but that is something I'm going to touch upon later. But it's an excellent question.
Thank you.
Okay, so what's another question?
I wanted to ask a quick question. I mean, you said that you're not using shape information, but can you actually infer the shape information from your policy?
So that's an excellent question, right? Maybe by the configuration of the hand, you can infer the shape information, right? I mean, that is possible, right? But what I mean is we are not providing explicit shape information to the policy for now, right? The other intuition we have had is that, because there are 5 fingers which are there, right? So it's an over-parameterized system. You actually don't need 5 fingers. I mean, even 3 fingers are sufficient to reorient the object, right? So because there are 5 fingers, there's a lot of redundancy in the system. And maybe that is also helping us, to be shape agnostic. But
yeah, I'm kind of wondering if you can use the system after you've trained it to reorient, if you can use it as kind of a sensing system that figures out the object shape without any vision sensors.
Yes, that's an excellent point. So actually there is a paper from Shubham from CMU. He is trying to do something similar, but maybe we can talk about this offline after the talk. I think it's an excellent suggestion. So, what I have shown until now is this control design, right? That I can design this controller, but everything is in simulation. So does this actually work in the real world, right? I mean, that's the question. So now, let's look at, prior work on transfer to real world. This was work from OpenAI. So they were in the simplistic setting of the hand facing upwards and having one cube, right? They were only orienting one cube. This is the system they used, right? What you see is these many, many, many different cameras being put around, which is what I mean by unrealistic sensing systems, right? Because you cannot have this on any real world robot. And why do they need it is to measure the states of the robot very accurately. So what we put out as a challenge is instead of doing this, we're going to do this. Just have a single camera over here. And from this single camera, we want to reorient the object. And so that's the challenge that we set upon. Now, what you notice is that our hand has become more simplified. It's no longer a 5-finger hand, it is a 3-finger hand. The reason is the hand that, this 5-finger shadow hand is first really expensive, but second, it keeps breaking every couple of weeks. So it's not really an experimental platform we can use for now. And this platform is, much more robust. It just lasts, it doesn't break, right? So now let's see how we can, what happens in this scenario, right? So until now, what I've told you is that we have trained this policy with state in the real world, and I go to actions. But then I also put something under the rug, which is this object current pose. How do we actually get the pose of new objects when there's severe occlusion, because now we only have one camera looking at the object, so the point cloud is going to be pretty occluded, right? So how do we actually get the object current pose, right? This must be inferred from the point cloud data. So now what we do is, well, instead of training a student policy from these states, we're going to train it directly from point clouds and also have joint positions as input. Right? Now this needs to work in the real world, so it needs to be fast. So we have a bunch of things to make things fast, which I'm not going to talk about, right? And then you also need some recurrence so that you can accumulate information over time. And we were able to get speeds up till 12 hertz on the system, right? So then what we do is similar. We train in simulation, right? So here is the goal configuration of the object on the top, and bottom is the hand, trying to reorient it, right? But maybe simulation results are not that interesting. Let's, move to a real world setup and see what happens, right? So first, I'm going to show you some examples where the reorientation is happening in plane. And what you find is that the motions the hand are making are not elegant, but it generally makes progress in the current direction, and when it gets close enough, it stops. Right over here is maybe another video, but this is a failure mode. But what you notice is the failure mode is not because the hand cannot reorient it. Many times it is because it does not know when to stop. And this is something that we're investigating why it is happening. But the one reason is that because of so much occlusion, it just doesn't know if I have reached the goal configuration or not. Then the system is robust to disturbances, right? For example, over here, tau is putting objects at different points, and the fingers manage to pull them in and still reorient the object, right? So you don't need to initialize the object in any special way. Then you can say, well, you only showed me in plane. What about out of plane, which is the more interesting case, right? So now if you have to reorient this object to over here, we need to reorient in a different plane. Now you're seeing these gray stickers. I mean, let me tell you, we're not using these gray stickers at all. This is more for evaluation. The camera just sees the point cloud, so it will not notice the gray stickers at all. Right. So okay, so what now is this system great? I think there's a lot of room. I mean, I wouldn't say it's great, right? I think what this is just like the first sign that we can train policies in simulation and then transfer them on the real world, right? And the fact that, I mean, is this a video that I chose? No, this is what we commonly observe. The problem that we observe is that we don't know when to stop, or the fact that the hand is very clunky in the way it is reorienting the object, right? So I will touch upon this, right? I mean, why is this happening, right? So, but maybe let's zoom out a little bit. So what I've shown is that first you design the controller, and then you're able to incorporate perception in the same paradigm, right? And then you might ask, why is this reorientation, which is transferring to the real world, but is also very clunky? So the one hypothesis is that our controllers are not just as good as they need to be, but the second also comes from hardware design, where the hardware we are using is pretty arbitrary, right? In some ways, right? I mean, first it only has 3 fingers, which means the redundancy is much lesser. Then it has no palm. Just imagine, just pick up an object on your desk and try moving it, right? You will notice how many times you use the palm. This hand is rigid. It has no compliance in it, right? So imagine if something was made of steel and you interact with an object, you make a point contact, things just fly off, right? So you really want some compliance so you can conform to the shape. There is no touch sensing, so you never know how much force is being applied. And even if you look at the finger shape, these are cylindrical, right? Which is not ideal if you want to apply forces in a meaningful way. Right, so there are problems at the hardware level which need to be resolved. So, because of this, we have a different thread in the lab which is trying to really design hands. right? So what I'm showing is, like a pipeline that we have developed for designing robotic hands. So I'm showing you 4 different hands that we designed. And these hands are 3D printed. And the blue things that you're seeing, these are almost like gloves that you can wear, and these are touch sensors, right? So, how does this work, right? So, our pipeline looks like, we construct the hand, then we deform the shape. Oops, here's the video. And then we put some sensors, and then we manufacture it, right? So we have a grammar of some parts which can be composed to design different hands. Then once we get a hand design, this is like the production of the grammar rules happening. Now I'm composing different grammar rules, and as we put them, we end up getting a hand design. So what this does is it enables the designer to very quickly explore many different configurations, which is a very tedious process right now. If you have to sit in the CAD program and build everything, that's very tedious. But now the shape of the hand may not be perfect, so you can go and deform the shape. And we are guaranteeing that anything that you do is manufacturable. So if you use our interface, any design you come up with can be 3D printed and can be assembled together, right? So then we put we get a design. Then we are specifying that, okay, we want touch sensors in some particular regions. So we choose how the stitch of the touch sensors needs to be, and then we pretty much say where these sensors need to be located, right? And then the touch sensing and the 3D printing goes to printers, and these things are printed. Now this is collaboration with some computational fabrication people at MIT. Now we got this hand. And this hand tries to cut something. If the forces are small enough, so it will cut it. So if you see the forces on the left, but if it is trying to cut acrylic, for example, the forces would be really big and the hand would stop. So if you see in the bottom, the hand actually stops, right? And it doesn't really goes and cuts the acrylic, right? So the hope is, now that we can design hands and this pipeline is completely computational, we can co-design both the hand and the control, right? So, we have been working towards it to some extent, right? So, for example, over here, I'm showing you, some designs of the hands which were made for the task that you're doing, right? So over here, we needed a small thing to rotate the cube, right? Over here, you need a different configuration, or maybe you need a different configuration over here, right? And these things you can go out and manufacture. Right? And this is work done in collaboration with a couple of people at MIT. So in some ways, we can use the same framework to also do hardware and sensor design. And I think what this problem really requires is a full stack approach where I can work on the control, the perception, and the hardware, because they all play into each other. Right? So to zoom out a little bit, right, we started with the fact that, okay, we want to learn low-level skills. And what I've given you is one specific skill, which is in-hand reorientation, and showed you how we can exploit the simulator in meaningful ways to make progress on this problem. Right, so now, again, I'll take a small pause, see if there are any questions before I move ahead. Yes.
I have a question. That's okay.
Yes.
So you said that in your previous slide, you had three components, one for the hardware design and one for the control design. And then you had the perception. And what I'm wondering is whether the perception and the control had direct interaction. So whether perception, and I'm guessing the analysis of the image was focused on the manipulation task that you were aiming at here, or was it just a classification, like classical image classification?
No, so the perception is trained with the same paradigm, right? So let me see if I can.
I'm asking just because, to understand whether perception was task oriented in the sense that it was kind of trained to focus on things that actually affected the ability to grasp objects, or just detect objects in the environment.
No, so for example, this is the perception system, right? This is a point cloud which is there,
Right.
right? And the point cloud is trained to predict the actions. So the perception is trained for control, right? So when I say the same pipeline, I mean, I'm using the same framework, right?
Oh, I see.
There is student-teacher training happening, right? We can design controllers, we can incorporate perception, we can also do co-optimization, but we're going to use the same underlying algorithms to do all of them, instead of developing separate algorithms for control, perception, and hardware. So that's
so
the
perception was not separate to a different component. It was just part of the input integrated. I see.
Yes.
I have another question.
May I have a question?
Yes.
Okay, it's kind of a comment maybe about the control design. There is some evidence that when people are grasping or making manipulations, there is a sequence of actions, but each part of the sequence, the movement of the fingers are coordinated. So all the joints are moving together in each part of the sequence. Okay, so then they're changing from one to another, but in each part of the manipulation, the fingers and the joints are coordinated. So I'm triggered to think about whether this knowledge can be integrated somehow in the control policy, so it will be easier to learn than learning from scratch.
Excellent question. I think it's an excellent question. I think there are ways to incorporate this prior knowledge, which is possible. For example, you could you could have some demonstrations if you could collect, and you could constrain your policy to be close to those demonstrations. But actually, I'm going to touch upon this, but I'm going to touch upon this in context of a slightly different system, which is locomotion, where
it's related. It's the same. Actually, it's the same idea. Right?
Yes. So I'm going to touch upon this, of what are the pros and what are the limitations of assuming it. So maybe I'll come to this question.
Okay.
So let me go into, so I mean, I showed you one thing which was in-hand reorientation, but let me, describe you how we can use a similar framework to go and resolve some locomotion problems. And I will try to address a question which was just asked, right? So now what we're going to do is take the same framework, but go and do locomotion, right? So current legged robots are great, right? We have all seen videos from Boston Dynamics, they're moving around. But one thing, to notice is, how do these agents walk, right? They're really slow, right? Just to give some context, compare it with this. Right? This is how locomotion looks in the wild. The question really is, how do we get here? Right? Our robots are nowhere close to what these systems are doing. If we just see how they're moving, it's, I'm just astounded every time I see these videos. Right, so this agile locomotion has been a topic of great interest, right? So this Boston Dynamics made a robot which could be faster than Usain Bolt, but this is on a treadmill, externally powered, and the robot is held by a lever. Great demonstrations, but cannot do it in the real world, right? Then there are demonstrations of fast systems. For example, Sang-Bae Kim's lab at MIT, they build this system which can jump over obstacles. But again, while the system is good, it is hand-tuned to this specific environment, and it remains unclear how well these systems would actually work in more general settings. But the question which we are really interested in is what about agility in the wild? Right? Now there is a lot of impressive work in quadrupeds traversing diverse terrains. Right? So they can traverse a lot of diverse terrains, but the way they do it is conservatively. Right, they make slow motions, and then they go in almost 2 feet or 3 feet are always in contact with the ground, which is so different than what we saw in natural locomotion. And the other thing to notice is that most of these systems are actually blind, right? So you might say, well, they are slow because they're blind, and maybe if we incorporate perception, they'll be better. But turns out not really, right? I mean, there are systems which incorporate perception. There's a lot of fantastic work from ETH in this area, but even then they are slow, right? So the question we asked is, why does agile locomotion in the wild remain challenging? We can get agility in, simplified setups, or we can get behaviors on diverse terrains, but it is conservative. We can't get a mix of both. So, what do we do? So, some of our hypotheses going into this was, maybe maintaining stability at high speeds is challenging. Maybe there's some modeling assumptions being made. Maybe these systems don't, most of them don't have vision. Maybe that's the problem. Or maybe it's a problem with the hardware, right? Maybe the hardware is broken. So we're going to address all of these problems, right? But we're going to start first with, let's see if, maintaining stability at high speeds is challenging, or, if modeling assumptions, are a problem. But, just to start, right, we're going to say, let's use an existing model-based controller, which is, similar to the comment which was, put in, like, what if there were some pre-specified waves of motion, which is what most of model-based controllers do, right? So we use this mini cheetah as the experimental platform. We have the camera, on the cheetah, and, it has 4 legs, right? So the pre-specified, model-based controller can walk, right? It can also walk on diverse terrains, right? So we said, okay, great. This is, very good work. It's also a robust system. Let's take this. This is not from our lab. This is from Sang-Bae Kim's lab. He designed all of this, right? And then we said, okay, we're going to see if we can anticipate the future and, do some agile tasks. This can be used terrain information for agility. This led us to this work, learning to jump from pixels, led by Gabe, who was a PhD student, and a bunch of collaborators, and also Sang-Bae. Right. So the experimental setup first was simple. Is, we have this robot which we want to cross gaps, and we're going to change the difficulty of this environment by varying the gap width and density. Our action space is, the velocity of the robot. So by modulating X, Y, and Z velocity, I can make it jump, and also yaw in how much the robot can turn. Right? Then the robot feet are going to make contacts. So, the left feet, LF, right feet, RF. And similarly, we have the hind feet, which dictate the contact state, right? So over here, the 2 legs, the front legs are in the air, so it's 0. The hind legs are in touch, so it's 1. Now, what we want to do is, given the camera, which is seeing the observations, we want to train a policy which will predict, these high-level velocities and contact states of the robot. And this gets fed into a model-based controller, which produces, these joint positions, right? And there's a low-level PD controller which produces motor torques. Now, this is existing work, right? So we took the system as is. This is what we were trying to do is, can we make these systems more agile? Because the system sees what is coming in the future, maybe it can adapt, and therefore it can be more agile, right? So, okay. So now let's see, what happens. So one possibility is, we take this depth image, we do some reconstruction of the height map so we know where the obstacles are, and then we do some planning. The problem is this becomes challenging at high speed. If the robot has to move fast, reconstructing the height map is just hard. And there are other reasons, right? The height map doesn't really have any information about texture, so on and so forth. And the height map is not going to be perfect, it's going to be noisy. So this diagram is highly simplistic. There'll be more modules over here which will smooth out the height map or make it noise-free. Right? So you might say, well, instead of going through this intermediate representation, we can try to directly go from depth images to predict actions, have some rewards and use model-free RL. Right? Now, the problem is that, while this is very good for deployment, it's really hard to train. Right? We tried training this, it doesn't work. Right? The one reason is that as the robot is moving, the camera is also moving, and which creates, these images which, move in, different ways. And the amount of noise we were getting, it was, we couldn't handle it, right? So then we said, okay, we cannot train this, but again, we're going to go back to the same idea. We can exploit the simulator, right? So in simulator, we have access to the height map. So we can train an RL policy from this, which is much easier, but we cannot deploy this. So we're going to train a student policy, right? Which takes the height depth images as inputs. And the idea is the same. Supervised learning is much easier than RL. So, we can do this, behavior cloning loss, right? So we can make the student match the teacher, right? So we use Dagger over here. Same thing that we did before, teacher policy, student policy, and this is the policy we're going to deploy. All right, so just some more details about the architecture. We have the depth image, goes as an input to a CNN, we get some latent Z. Then we include some proprioceptive state, right? Body orientation, body velocity, blah, blah, blah. And then we predict, the action. Right? So now let's look at the action prediction for a moment. So the action prediction has, two components. So let's look at the first component in purple first, which is, the 4 velocities of the agent. Now this is over here, what is called as a fixed gate policy, which is common assumption in prior work. Now, what do I mean by gate? By gate, I mean, we have some knowledge of how should different feet move, and they are synchronized. So this is one example of a gate which is running trot. Here is another example of a gate which is bounding. So as you see, the legs are moving in a synchronized way. Right? So first, what we're going to do is just to change the velocity of the robot, but let the gate be fixed. That is how the legs, the relationship between the legs motion is fixed. We're just changing how fast the system is moving. Right? And the reward we're going to use is, how much forward progress the system makes. The action should be smooth, and maybe don't run too fast. Right? At training time, we're going to sample, different configurations of the environment. So these are, some different episodes, and then see what happens. Right? So first, let's look at, what a system does. So these are first results in simulation. So what you find is, the system can, jump over gaps, which, looks promising. So let's go and try to quantify the performance. So what I'm showing on the y-axis is the gap crossing success rate, and on the x-axis is the gap width. Just for reference, we have blind policies which don't have access to vision. Of course, they would do really bad. Now with fixed gates, we can actually compute the ideal distance which you could cross, which is ideal trot and ideal prong. Now what we find is, we can meet or get close to the ideal limits. Now you might say, well, why is the vision trot going up, beyond the ideal? Because, there's some reasons where the trot is not really a trot. But anyways, the point being, we can, get close to the limits, the theoretical limits, which prong and trot have, right? But if we were to put this in context of what is happening, the robot's body length is actually 40 centimeters, but we're only able to cross gaps which are less than 40 centimeters. It's nowhere close to the kind of agility I promised before, right? So what's going on? Right? So what's going on is that we have really limited the robot's motion and how to move its leg by keeping the gate fixed. So now we're going to also let the gate change by deciding, when the robot's feet are going to be in contact, right? So we are also going to predict, which feet should be in contact. So which is what leads us to this variable gate policy. Now, when we deploy it, in simulation, you can see it feels much more agile. It can cross, longer gaps, right? So by freeing this assumption and letting the system decide how to move its legs, we can actually have this blue line, which can cross much longer gaps, much more than the robot's body length. Now we can take the system, try deploying it, in our lab environment first. Here is one example, here is another example, system trying to cross those gaps, right? So, in some ways, this was our first attempt in trying to use the same framework, the student-teacher framework, to try to do perception for these quadrupeds. But if you, notice the videos I showed you, you might have said, well, wait a minute, there was a difference. The real-world gaps look much smaller than what I showed you in simulation. And this is actually true, right? Like in simulation, we could maybe cross, 54 or, 60 centimeters gap. But the best real-world performance we could get was only 26 centimeters. We couldn't cross gaps beyond it, right? They were like, why is this happening? So we, ran a series of tests and investigation. What we found is that this model-based controller relies on body velocity. And to estimate the body velocity, there's an assumption which is made that there is no slip between the foot and the platform. But at high speeds, it doesn't hold true. The robot is slipping all the time. right? And therefore this MPC just breaks down, right? It is possible to fix it. But then the other things which might come up, right? At very fast speeds, the motors might behave differently. They might not be in the linear regime. There are other things which keep coming up. So it's a long tail of problems. Now, I think it is possible to fix all of these problems, but it takes months to fix each one of them. So what we wanted is something which is more scalable instead of, as a human designer, finding each problem and debugging them. So what we decided was to let learning figure it out. So replaced our model-based controller with model-free controller, not because model-based controllers cannot do something, it's just because they are not as scalable as what we think model-free control could be, right? So now we're going to design the controller in a similar way, which is going to train in simulation and then transfer these policies trained in simulation to the real world. So a nominal policy trained in simulation looks like we have some states, we predict some actions, we maximize the sum of rewards. Now, typically in simulation, we have to assume some simulation parameters, for example, some friction, some robot mass, so on and so forth, which I'm going to call as nominal simulation parameters. The outcome is a policy called as a nominal policy. Now let's look at how this, the top speed of this policy looks like as I'm varying the friction. Right. Why I'm varying the friction? Because I don't really know the real world friction. So I really care about the performance of the policy across a range of frictions. So what you find is that the nominal friction, the policy does quite well. As the friction increases or is different, the performance drops, right? The performance drop on left also happens, but there's another reason why it happens, because at low frictions, you really can't, run that fast, right? So we would focus mostly on the right part of this curve. Right. Then the typical approach to deal with this problem is domain randomization, where we try to train this policy, but we try to take an expectation over different values of domain parameters. For example, we can sample ground friction from some range, mass from some range, because we don't know exactly what it is in the real world, and then train a policy which is robust to different parameters. Right, which is called as domain randomization or DR. So now let's plot the DR policy. So what you find is that it is transferring better at frictions which are different than the simulation, but at the nominal friction, the performance is worse. Right? So the transfer is better, but it is more conservative. The reason this is happening is because we are trying to average over domain parameters. We are not aware of how the domain looks like. So, what if we fed the domain parameters as input to the policy, right? Which is, you have the state, but also what is the friction, what is the mass as input, and then we predict the action. And this information is, again, privileged simulation information, available in simulation, not in the real world, right? So we can now train this policy, which is what we're going to call as the teacher policy. And as the story has been, this teacher policy does very well, but it's something we really cannot deploy. So, we want to find something which we can deploy, right? So then we have a student policy, which we are going to deploy. And the idea is we're going to infer, what these simulation parameters are going to be from a history of state action observations, right? And the way this is trained is the same. We do behavior cloning of the student, and we get the student policy. Now, if we compare performance, what we find is the student policy, closely matches the teacher. It does well at the nominal value, but also works well as the parameters are different. Now, this way of using student-teacher learning for online adaptation is, has been around, or this idea has been developed in a couple of other works as well. Right. So, okay, so maybe in interest of time, I'll skip a few details, but let me just tell you what the the state space looks like, right? So we have a joint positions, joint velocities, the body orientation from the IMU as input, actions are joint positions. Then we have a history of past actions and some command velocity. And, then we predict how the robot is going to move. Right? So what I'm going to do is, I'm going to jump to, some, results of the system, right? And the Yeah, so let's see what the system ends up doing. Right. So first, this is running the system, in the lab. We recorded speeds of 3.9 meters per second, which are the highest speeds recorded, on this system, in any setting. Right. Then, I'm going to. We can also, take it on, more challenging domains, right? For example, here, it can not only run fast but also spin. This is on ice, which is very slippery. And we can take it on, other terrains, right? So I'm showing on the left is the MPC controller. At some point it is trying to climb the gravel, it kind of stops. Again, the message is not that one cannot build a better MPC controller. What we feel is you need to tune the MPC controller per environment. So this is, what, our system ends up doing, right? And it can both, run, spin, right? There are more videos, but, sometimes some things unexpected can also happen, right? Over here, this robot is running, but screw from one of its motors came out. So if you see the leg, it's actually limping, right? But it still keeps on walking, right? It doesn't really, fall down. And so in some ways, we can use the same framework and again go back and improve the controller. So now a controller can work in the real world, is agile, doesn't have vision in it, right? So what we're looking at is, now that we fixed the MPC problem, we're going to integrate both control and perception. But the other part is also hardware, right? If you look at these systems, if you look at these, quadrupeds, all of them have these ball joints which make contact with the ground. Why they are ball? Because the balls make point contact with the ground, which is easy to model, right? But just imagine if you didn't have ankles, how hard it would be to walk and run. It's much harder, right? It wouldn't be as agile, right? So what we're investigating is how we can co-design these ankles, for the system. This is work in collaboration, with some mechanical engineers and students, right? So, and then, you can say, well, what happens if we get a new robot, right? Turns out we can get a new robot, which we got one of them. And within 1 week, we can replicate everything that I showed you, right? So in some ways, the system is really scalable, right? So to summarize, what I presented you is a framework in which we looked at 2 different problems using, student teacher learning. So, we work with the same simulator, same paradigm. And one thing which is important is this idea of curriculum learning. So even to get this agility, we did require curriculum, which I didn't have time to look into. There are tons of open questions, right? And, I'm happy to discuss them after the talk. So to summarize, what I showed you is how to learn low-level skills for 2 different problems, how to do it in a full stack way and in a way which is scalable, and which we feel is going to be a big part of a dream to have robots, do things that we ask them to do. So with that, I'm going to stop.
Thank you, Pulkit. Very, very exciting talk. Any questions from the audience?
I have another one, if that's okay.
Yes, yes, please.
So you said can you go back to the slide where you were showing us the controller versus the model-free approach? And you said that since the controller failed to, it's pretty cool. I kind of recognize all the locations where you filmed these videos, so I'm very exciting. Anyway, the controllers were, you said that the model-based controllers failed, and that's why you actually switched to using a model-free approach. Couldn't you use actually the models as a base or as a prior to training process, instead of just setting them aside, starting to learn from them and just tuning them and learning how they operate?
Yes, so that's an excellent point. So we have done, we have looked at that problem in a different context. For controlling some micro robots, right? We learn the residual. We start with a model and just learn the residual. right? But it really depends, right? It depends on what is more complex. So suppose if your model was linear and you were trying to learn a non-linear function, then most of the complexity is going to be in the residual. So at that point, the benefit you get from the model is very small. But if the model is complex and the residual is linear, maybe then that approach works, right? So I think it is problem dependent. And the second thing which happened for us is we were not really training in the real world. We were training everything in simulation. So in some ways, those differences are not a major thing for us right now, right? If it trains in 3 hours versus 2.5 hours,
Then the quality of the data that you use really depends on the quality of the simulator, right? The model is still there, but it's there in the simulator.
Yes, so the model is still there, right? We cannot escape models. The models are in building the simulators, right? So the point is not saying that don't have models. The point is have models, but let's use them in a different way.
Thanks.
May I ask a question?
I think we have one last question because it's already 4 o'clock, and then we can take it offline or just remain in this room.
Yeah, I mean, I have some time, so I'm happy to hang out, for some time if people are interested.
Okay, may I?
Yes, please.
Yeah, go ahead.
Yes, thank you. So in the reorientation task, we can, I think, correct me if I'm wrong, but we can look at the different objects that we're reorienting, different tasks within this domain. So this is kind of leaking into the territory, right? Am I right?
Sorry, your voice was breaking up, so I'm not sure what exactly was your question. Repeat
the question. Do you hear me now?
Yes.
Great.
Yes, I can hear you now.
Yeah. So what I'm saying is that in the reorientation problem, what I see is that you were able to generalize into many different objects. Now the question is, do you require? Were you? Maybe I missed this, but were you able to actually use objects that you've never seen without any more training or any more training?
Yes. So all like we never trained on YCB, for example, right? So we were showing results, and all the results on YCB were without training on YCB.
Yeah, and so I don't think I understood how this generalization is was in your learning model, where it comes into play.
So it comes into the play because we are training on a lot of diverse objects, right? So we train on 2,000 objects, right? Which are almost, there's a data set which exists, which is somehow some pseudo random generation of object shapes. You train on them, and then you transfer to new real world objects.
So it's almost IID, the object shape.
I mean, that's the assumption, yes.
Okay, thank you.
Right, so let's thank Pulkit again for a very exciting talk, and let's stay online if you want to ask more questions. Thank you, Pulkit.
Well, thanks, Avi, for inviting, and thanks everyone for coming. I'm happy to stick around if people have more questions.
Thank you very much.
Thank you.